My name is Gautam. I'm an assistant professor at the Department of Mechanical Engineering. Today we are going to see how to conduct the experiment, that is to determine the Young's modulus of a given specimen using a strain gauge. Okay, first let us see where strain gauges are used. See, strain gauge is a very critical member in measurements part of the realm, where any measurements that you have to take in case of if you're measuring the weight of any object, so it has to be measured accurately. For example, if you have a consignment and the consignment weighs about 100 kilos and the consignment comes into your company, and how do you know it is 100 kilos? Obviously you have to weigh it, and we can't. In the olden days they used to use scales where you put weights on one end, put the material on the other end, and then use to weigh it. Okay, those are technologies where it is outdated. Okay, nowadays we use strain gauges. Strain gauge, basically it's a more of a digital indicator where you put the load on a scale and the scale gives you certain readings. Okay, so but how do you know whether the reading is correct or not? So you have to calibrate even strain gauges. So as we all know, stress is a very important factor in any design experiment. But can we measure stress directly? No, we can't measure stress directly. We can measure the consequence of a stress. So what is the consequence of a stress? The consequence of a stress is deflection. So we can definitely measure deflection. Okay, but how do we measure deflection? Okay, so a person by the name Lord Kelvin, okay, he actually came up with an experiment where the electrical resistance of a wire changed with a change in diameter and length. Okay, so he came up with the setup where the application of this was migrated to many other places. So in this experiment we are going to use the same concept. So the Lord Kelvin said that electrical resistivity changes with the application of load when there is a change in length and diameter of the specimen. So the same thing we are going to use here. As you can see, this is a cantilever beam of certain specimen. This specimen is of certain length and dimension, and we are going to attach a load to it, and we are going to calculate the bending stress. And this is one of the basic equations in your in your engineering strength of material subject or mechanics of material. You probably would have done this experiment even in your tensile stress in your third semester material testing lab. So we all know what Young's modulus is. Okay, in an elastic specimen, when stress is proportional to strain, there is a constant. Okay, when you remove that constant, we get nothing but Young's modulus. That is, we have capital E equals stress divided by strain. So within elastic limit, okay, the stress is directly proportional to strain, and when we plot a graph, when we take the values of stress and we take the values of strain, when we plot a graph, the graph should be a linear line. Okay, and when we take the slope of it, we get Young's modulus. Okay, so this is how we determine the Young's modulus using a strain gauge. So basically we have a specimen and we put a load, and when we put the load, there is a deflection in the specimen. It's very simple. You take a steel ruler, not a plastic ruler, steel ruler, and you put some pressure on it. You can see a deflection. Deflection is nothing but movement. So we can record the movement. What is happening is, when we are putting the load here, there is deflection, that is there is change in either length or certain dimensions, and we are recording the electrical resistance. This change in electrical resistance is transferred as the electrical signal, and we get different readings. Okay, so the aim is to determine the Young's modulus of a given specimen using a strain gauge. So you all got to know what a strain gauge is. We all got to know the working principle behind a strain gauge. So what is the apparatus we need? Strain gauge indicator and strain gauge based cantilever beam, and you need weights. Okay, so what is the observation that you need to initially do? Okay, the observation is you need to find out the length of the specimen, the breadth of the specimen, and the thickness. So once we get all these values, then we go and set up with the experiments. So the data that we will be recording in the experiments are, first we have to put weights on the scale. So we put different weights and then we find out, we look at the digital, we get the readings from the instrument, and we find out the indicated strain. Okay, once we get the value of indicated strain, you divide that by 4, you get the bending strain. And finally, since we have all the values from the observation, we can get strain by using the formula. Sorry, we can get bending stress by using the formula sigma equals 6 into WL by BT square. So ultimately, we'll be getting the values of stress and we'll be getting the values of strain. And Young's modulus can be determined by plotting a graph of stress versus strain. You get a linear line and you take any two values based on your scale. You draw two lines, a horizontal line and a vertical line, and then you find out the slope. So this is the theoretical part. Let's move to the experimental part. Okay, so now what you're looking at is the experimental setup of the strain gauge. So basically, as I explained in the diagram, we have the beam. This is the cantilever beam, and there's a provision given for weights to be added. Okay, so we have to calculate the bending stress. And one thing that you have to note on this instrument is there's a reading, there's a decal which is called as strain. So the knob should always be pointed towards strain, okay, not towards EXE volt or MV output. It has to be always pointed towards strain, and this knob should be pointing towards read. These are two things that you have to keep in mind. And basically this is the reading where we get, and this is in micro strains. Okay, so first let us, as we said in observation, the material that the specimen is made up of is aluminium. Okay, and we have to find out the values such as thickness, length and breadth. So let's find out the thickness using a scale, sorry, the length using the scale. So we measure and it comes up to 300 mm. Okay, you can see it on the scale, it comes up to 300 mm. Okay, similarly we are measuring the breadth. So it's pretty straightforward, it comes up to 50 mm. Okay. So then we are measuring the thickness using the vernier caliper. So it comes up to 4 mm. The readings are very bit small, so I'm going to give it out the reading. And during your examination, you have to use a vernier caliper to measure the thickness, and the thickness value here is 4 mm. So now, as I said, we need to, as stress cannot be directly measured, the consequence of stress is always measurable. Here the consequence of stress is the deflection. So as I said, when I put load, there is a deflection, and that deflection is transmitted to the digital reading as a electrical signal, and that gives us the reading. Okay, first make sure, before you start the experiment, make sure you have 0 reading. Okay, and this knob is to calibrate it to 0 reading. You have to be careful, it is very sensitive, so please take your time and try to get it as close to 0. Okay, now first thing is we add weights. These weights are in increments of 100 grams. So the main objective here is add weight. So once we add weight, there is a deflection in the beam, and that deflection gives an electrical signal based on the resistance developed in that particular beam, and then we note down the value. So we've added 100 grams and we are getting 102. So next we are going to add one more weight and we are going to note down the reading. Okay, next we have added another 100 grams. So now we have to note down the reading. And third, we are going to add another weight. Okay, and now we are going to note down the reading. So this is the experiment, and we're going to tabulate the values. Okay, we just saw how the experiment was set up and how to set up the experiment, how to take the values. So now we are going to substitute those values into the tabular column. It is pretty straightforward. So we got the values. What we did in the experimental setup was we added weights. So we added weights in increments of 100 grams. So we are going to convert 100 grams into kgs, and we are going to take that, convert it into newtons. Okay, so it's pretty straightforward. And once we get the values of the weights in newtons, then we're going to see the readings that was taken in the instrument. The readings are in strain microns, as we saw in the instrument panel as well. It is in strain microns, and we got the values 103, 108 and 117. Okay, next we divide that by 4. You might wonder why by 4. That is nothing but the bridge constant. You don't have to worry about it. That is more into the electrical setup on that instrument, where it's called a Wheatstone bridge. The Wheatstone bridge, when we use a Wheatstone bridge, it basically has 4 resistors, and that's why we divide this bending strain by 4, and we get this bending strain in microns, and these are the values when you divide this value by 4. And ultimately, we need to find out the bending stress. So the formula for bending stress is sigma equals 6 into the weight that is added in increments of 100 into length of the specimen divided by the breadth and thickness squared. So it's a pretty straightforward formula. We have all the readings. We have the material of the specimen, that is aluminium. We have length 300 mm. We have breadth 50 mm and thickness 4 mm. Where did we get these values? We got these values from the experimental setup, where we used a ruler and a vernier caliper to calculate the length, breadth and thickness. We substitute these values into the formula. We have bending stresses 6WL by BT square. W is the load that we put in increments of 100, and we have converted it into newtons. And length is length of the specimen, breadth and thickness. Once we substitute the values, we get the bending stress in Newton per mm square. So we tabulate for different values, and then once we get all the values, we plot a graph of stress versus strain. And once we plot a graph of stress versus strain, you can take a slope. Okay, as we all know, when you have a proportionality limit, you always get a linear graph. In a linear graph, we can plot the slope. We can get a slope by plotting the by having a horizontal line and a vertical line based on the scale, and you can calculate the slope anywhere on the elastic limit. And this is how we get the Young's modulus. Thank you guys.